the grand scale. Now we're going to hear about a specific research project where apparently AI played a very important role. So I'll have Andru Gheorghiu.
Yeah, thanks Anand, and yeah, thanks for having me here. It's always a pleasure to be back here. Yeah, so as Anand kind of mentioned, this talk has two parts to it. So in the first part, I will tell you about a result on constructing pseudo-entangled states in constant depth. And then the second part will be kind of the backstory of this result and how I used AI to kind of help me write the paper. So before I go into that, I've used AI in everything having to do with this project, including creating this talk. And I asked it for some suggestions for a good title. And I want to show you some of the runner-ups that didn't actually make it as the titles of this talk. So do androids dream of constant depth circuits? An AI-assisted story? The proof, the whole proof, and nothing but the prompt? The result and how the bot thickens? And probably the one that was like the closest to being the actual title, which is I asked an AI about pseudoentanglement. You won't believe what happened next. So I showed these to Daniel the other day, and he said, it's funny in a you ask your uncle sort of way. Okay. So before telling you about pseudoentanglement, let's maybe start with something that I assume most people are familiar with, which is pseudorandom states. So these were introduced by Ji, Liu, and Song in 2018. So what are pseudorandom states? So they're efficiently preparable quantum states that are computationally indistinguishable from hardness states. So if we want to be a bit more formal, efficiently preparable just means that there's a polynomial-time quantum algorithm that, given some classical information, let's say k, which stands for key, so given this key, it's able to prepare the state phi k from some family of pseudorandom states. And computationally indistinguishable from hardness means that if you take any polynomial-time algorithm A and you give it polynomially many copies of either the pseudorandom state for like a randomly chosen key or polynomially many copies of a hardness state, the algorithm is unable to tell you which of these two it received. So like the probabilities of it outputting, like guessing correctly in the two cases are negligibly close to each other. And we know many constructions of pseudorandom states from standard cryptographic assumptions. So in particular from like the existence of one-way functions, which is one of the most basic primitives that we have in cryptography. And just to show you like a quick example, so one thing you can do is you can create an equal superposition over all n-bit strings, and then to each component in the superposition we'll apply a phase where omega n is the 2 to the nth root of unity, and this f sub k of x is what's called a pseudorandom function. So this is like a standard object in cryptography that you can get from one-way functions. You should think of it as just like some sort of like random-looking function. And you can prove that this family of states does indeed satisfy these properties of being pseudorandom. So pseudo-entangled states are very similar in spirit, except in this case we have two family of states, which I'll denote as phi k and psi k. And you see now that the key k that will instruct you on how to prepare the state can come from either a set which I'll label L as in low entanglement or H as in high entanglement. And just to give you some intuition before I show you like the more formal definition. So the idea is that if you imagine that these two graphs represent quantum states where the vertices are qubits and the edges are entanglement between the qubits, then what you would do is you would fix a bipartition of the qubits. So you split the qubits into a set A and its complement. And then what you want to know is how much entanglement is between these two partitions. And in one case, the entanglement will be very high, kind of illustrated here by having many edges going across this cut. Whereas in the other case, the entanglement is very low. So there are like very few edges going across the cut. Yeah.
This is a cartoon, right? In the sense, I mean,
Yes.
it's a cartoon, but
Yeah.
it's also a very, you're not talking about two-qubit entanglement. You're talking about macroscopic entanglement, right?
No, I'm actually talking about von Neumann entanglement. Yeah, like bipartite entanglement.
Yeah, but von Neumann entanglement between large parts of the system, not between, like if you're talking about n-qubit system, you're not interested in two-qubit entanglement.
Correct, yeah.
Yeah, but still, we're not seeing.
Yeah, it's like literally partitioning the qubits into two sets.
Yeah.
And
you're not going to see the entanglement if you just look at reduced density, just the two qubits, right?
Sure, yeah. I mean, I'll just show the formal definition in a second. So you want these two situations to be computationally indistinguishable in the sense that if you're given many copies of this state or many copies of this state, you can't tell whether you're in the high or the low entanglement case. So let me make this a bit more precise. So again, efficiently preparable just means there's a polynomial-time quantum algorithm that given a key, if it's from the low set, then it creates the low entanglement state. If it's from the high set, it creates the high entanglement state. And so the notion of entanglement that we're looking for is you split the qubits into two sets, like A and its complement, and then you just look at the reduced density matrix when you trace out part of the system. And then you just look at like the standard von Neumann entropy for these reduced density matrices. And what you want is that there is at least a constant gap between these two entropies. So like one state should have at least constant bits more entanglement entropy than the other state. And this cut is specified to you in advance, like you know what the cut is, like what the bipartition of the qubits is that you're considering. But nevertheless, the claim is that it's still hard for you to tell whether you have high or low entanglement. And just as before, this is encapsulated by saying that any polynomial-time quantum algorithm, given many copies of either the low entanglement state or the high entanglement state, is not able to tell you which of the two was given. Let me maybe just pause for a second if there are any questions about the definition. Okay, if not, so let me tell you a bit about similarities and differences between pseudorandom states and pseudoentangled states. So both of them seem to have like applications in complexity theory and cryptography, and potentially in quantum gravity. This was kind of the motivation for introducing pseudoentangled states, though I would say that part is maybe less clear at the moment. And both of them are achievable from standard assumptions. So I didn't mention this on the previous slide, but just like pseudorandom states, pseudoentangled states can also be constructed from one-way functions, so from like very basic cryptographic primitives. But now we can talk about some of the differences. So pseudorandom states are somewhat analogous to pseudorandom function, like we even saw that construction from pseudorandom functions. Whereas pseudoentangled states, I don't know if there's a good classical analog, but one that you could consider is what's called distributional entropy testing, which is the task of being given samples from some probability distribution, and from those samples trying to estimate what the entropy of that distribution is. So that's somewhat analogous maybe to pseudoentanglement. But now a difference that is kind of significant is that for pseudorandom states, by definition, the key must be secret, because you're claiming these states are indistinguishable from hardness, but hardness states have exponential circuit complexity, whereas pseudorandom states by construction can be constructed by polynomial size quantum circuits. So if you knew the key k, like if this was revealed to you, you could immediately test whether the states you were given are like the low complexity states or not. But interestingly, for pseudoentangled states, this is not the case. So even if you give out, like there are constructions where even if you give out the key that prepares the state, you can think of this as like I just give you the circuit that prepares either the phi states or the psi states. It could still be computationally hard for you to tell whether this circuit is producing a state with high or low entanglement across a cut. And this is referred to as public key pseudoentanglement. So in this paper where we kind of sort of considered an analogous notion, implicitly our results had this public key property, and then this was formalized in this later paper by Buland and others. So, formally what this means is that if you have a quantum algorithm that is trying to distinguish between the two cases, even if you give it the key that prepares the state, it can't tell whether it was given a key from the low set or from the high set, basically. Like these keys look somehow indistinguishable for the two sets. And finally, the subject of this talk, so pseudorandom states cannot be prepared by constant depth circuits because we have this result by Huang et al. Showing that the circuits that prepare, like if you're given a state that was prepared by a constant depth circuit, with polynomially many copies of that state, you can learn the circuit. Or at least you can learn a circuit of constant depth that can prepare that state. And that means that you can distinguish it from hardness. But interestingly, like what I'll basically talk about is that it seems that pseudo-entangled states can actually be prepared with like purely constant depth quantum circuits. And in fact, as we'll see, like geometrically local, like 2D local constant depth circuits with just single and 2 qubit gates. So this implicitly means that this construction is public key because even if you don't give me the circuit, I could just learn it from polynomially many examples using this Huang et al. Result. So necessarily, this construction has to be public. Okay, and yeah?
Can you say a little bit about the applications of pseudo-entangled states to complexity?
Right, so it has applications, I guess, in property testing. So I'll talk a little bit about this later on, where from these states, you can prove the hardness of various tasks. For instance, the task of learning ground state entanglement structure for local Hamiltonians or things like this. So like property testing were like learning tasks.
And is it like once you have hardness of those, that gives you crypto?
That's true, yeah. So there have also been results showing that if you have such states, then this also implies certain crypto primitives that you can get from those states. Any other questions? Okay, if not, let me just say like one quick word about the model. So as I said, like the circuits that we will use will be just standard quantum circuits with single and 2 qubit gates. The depth will just be the number of layers of gates that can be performed in parallel. And the construction will be constant depth, so strictly speaking QNC0, and will be 2D local. So I just want to clarify this just to say that we won't be using unbounded fan out or unbounded fan in. Like it's not going to be QAC0 or something like this. It's really going to be QNC0. Okay, so before I tell you about, yep.
Like it's easy to do if it's not 2D level?
No, so yeah, it's not easy to do, at least like it was hard for me to do it, even if I didn't have this restriction. Like initially I wasn't even thinking about geometric locality. But then I wanted it to be geometrically local to be able to get these applications to like hardness of learning ground state structures of local Hamiltonians. Because that will then, like I'll show this, it will just follow immediately from the fact that the circuits preparing these states are local circuits. Okay, so let me first tell you like one way in which you could create pseudo-entangled states. For the moment, let's forget about constant depth, like just in general, how would you do it? So here's one way. So suppose I have two functions, f and g. So these are just purely classical functions. And we're going to require that they're efficient to evaluate. So we have polynomial-sized classical circuits that can evaluate these functions. And we're going to assume that f is a 2-to-1 function. And what this means is that for every output of the function, so every y in the image of the function, there are exactly two distinct inputs that map to that output. So f of 0 equals f of x1. F of x0 equals f of x1 is equal to y. whereas the G function is injective, so it's a one-to-one mapping. And finally, suppose I can come up with such functions that are computationally indistinguishable from each other given the circuits that evaluate them. So if I give you a circuit that evaluates either the f function or the g function, from this circuit description, you're not able to tell me if you were given the 2-to-1 function or the injective function, based on some cryptographic assumption. So then if you have such a pair of functions, you can do the following thing. You can simply evaluate the functions in superpositions over all inputs. And then we just consider a bipartition of the qubits across these two registers. And we can see that because f is 2-to-1, it's only going to take half of the values corresponding to the size of the input, whereas because g is injective, it's going to take all the values. So that simply means that if you trace out, let's say, the second register, then in this case, the state that you'll get will be totally mixed on the entire input space I, whereas in the F case, it's totally mixed only on half of the input space, not on the entire input space. And so this means that, for instance, if that input space is of size 2 to the n, then in this case, that density matrix has n bits of entropy, whereas in this case, it's supported on only half the size of the system, so it has n-1 bits of entropy. So therefore, the difference in entanglement entropy between these two states is exactly 1. It's like 1 bit of entanglement entropy difference. And of course, if f were many to 1, like let's say it's a 2 to the k to 1 function, then the entropy difference would be k instead of just 1. And we know how to come up with such functions. Except that the constructions that were known prior to this work were functions that you could implement with logarithmic depth classical circuits, or constant depth circuits, but with unbounded fan-out. And actually, there's a little bit of a story here, which is that we, like myself and Matti Hoban, had this paper in which we kind of put out this result, and we claimed that we had this pseudo-entanglement notion in constant depth. But we didn't realize that because the classical circuits were using unbounded fan-out, that means that quantumly you kind of inherit this unbounded fan-out in preparing these states. So it wasn't like truly QNC0 circuits. It was like QNC0 sub F, like QNC0 with fan-out. So then we, amended the paper and then started thinking about, can we get something that's like truly QNC0? Okay, so in this case, we'll consider functions f and g. So I'll make a specific choice for what these functions are that are of the following form. So the input space will consist of n-bit strings whose Hamming weight is t, where you should think of t as much less than n. So for now, I'm just going to show you this abstractly, and then I'll give you intuition about what all of this means. The output space will consist of m-bit strings, where m is less than n, so like less than the length of the input bit of the inputs. And the functions we're going to consider will just be linear functions mod 2. So f of x will be a times x, g of x will be b times x, where a and b are binary matrices, so m by n binary matrices. And all of the operations are mod 2. So like addition is mod 2, it's an XOR, and multiplication is, it's just multiplication because it's the same. So here's the intuition. You should think of A and B as parity check matrices of a classical linear code. You should think of X, like the input, as a low-weight error. And you should think of the output of the functions as the syndrome that you get from applying the parity check matrix to the error. And what I will require is that the A code is what I'll call a bad code, meaning that it has a lot of degenerate syndromes. So for every syndrome that you get, there can be many possible weight t errors that correspond to that syndrome. So in particular, you can't really decode with this code. But on the other hand, the B code is a good code in that it can correct all weight t errors. And so this means that for the B case, the function is injective. Like for each weight t error, you will have a unique syndrome. And what we'll need is that these A and B matrices are indistinguishable from each other. And in fact, the A and B matrices will just look like completely random matrices. So they will just look like totally random n by n matrices. And by just looking at them, you won't be able to tell if you were given the good code or the bad code, essentially. And note that, kind of obviously you're not given the decoding algorithm, because if you had the decoding algorithm, or if there was an efficient decoding algorithm, then you could just test to see if you're able to decode or not. And then you could tell them apart. So this is possible based on this recent result by Dao and Jane, where they introduced this very nice cryptographic assumption called dense sparse LPN. I won't go into too much detail about what this is, but you can ask me about it if you want. I think it's a very cool construction, and it's very closely related to like standard LPN, if you've heard about this. So it's called the learning parity with noise problem. And the paper is even called lossy cryptography from code-based assumptions. So code-based assumptions because we're making an assumption about the existence of certain codes, and it's lossy because we're saying that one code is lossy, like it kind of loses information about the error. Like when you apply the parity check matrix, you get a syndrome that could have corresponded to many other different errors, whereas in the other case, this doesn't happen, and yet the two cases are computationally indistinguishable from each other. Does this make sense? Are there any questions about this? Yeah.
Is this at all related to pseudorandom codes?
That's a good question, but I don't think so. At least I'm not sure if you could get pseudorandom codes from this, for instance. In particular, like, or maybe you can. So this B code will have an efficient decoder, but there's like some trapdoor that you need to know in order to be able to efficiently decode. So maybe it is related, but I'm not sure. I haven't really thought about it. Any other questions? Okay. So then here is our goal. So as before, we just want to create a superposition over all inputs from our set. So in that case, this means all n-bit strings with Hamming weight t. And then in the second register, we'll just compute m times x, where m is a binary matrix, and it's either the good code or the bad code. So one thing we can do to make our life a bit easier is instead of creating this superposition over weight t strings, we can actually just substitute this with a binomial distribution whose expectation is exactly weight t. So by this I mean, imagine that every qubit from this x state, so this x state will just be a product state, and every qubit will be biased towards 1 by square root t over n amplitude, and biased towards 0 by 1 minus t over n amplitude. So in expectation, if you take the tensor product of all these states, you will have a binomial distribution that's centered around weight t strings. And you can show that this doesn't change the entanglement entropy across this cut very much. Like it changes by a very small amount. So it's fine for our purposes. So that's nice because then, this state we can just prepare in constant depth. It's a product state. You just need to do like y rotations on each qubit to create this state. So really the problem is preparing this register like m times x. So in general, this is not doable in constant depth. Intuitively, this is because every output bit here depends in principle on like all or like most of the bits of x. So then you have like, each bit of this register interacting with pretty much all of the bits of this register. And you can't, like, you might be able to parallelize it a little bit, but in general, especially if M is a dense matrix, which it will be in this case, you're not able to do this in constant depth. So to get around this issue, we're not going to prepare this state, but we're going to prepare a state that's equivalent to it. And I'll explain what I mean by equivalent, but morally it will mean that it's still encoding the same information as m times x, and therefore the entanglement entropy across the cut will be pretty much the same as if I had prepared this state instead.
Is it known that sparse matrices of this form don't exist?
Yeah, so that's a good question. So if the matrix is sparse, then you get an LDPC code. So it's like always a good code. Now, you could try to engineer an LDPC code that's bad, but I don't know that you can make the two cases indistinguishable in the sparse case. At least to my knowledge, I don't know if that's possible. Yeah?
I guess I was just wondering, shouldn't the zero always just like assume a continuous gate set? Like you can, or what's the, do you have thoughts?
Oh yeah, so this is a good point. So yeah, for this result, I am implicitly assuming a continuous gate set. I don't actually know if it works with a discrete gate set. One way in which you could make it work is if you could take this t to be linear in n so that this becomes just a constant.
Sure.
But for the specific construction from this Dow and Jane paper, t scales as square root n, unfortunately. So that means that as n increases, the rotation has to be smaller and smaller, but only like inverse polynomially. Yeah. Any other questions? Okay, if not, so let me explain just one more concept from cryptography, and then we will be done. And that's the concept of randomized encodings. So this was introduced in this very nice paper by Applebaum, Ishai, and Kushilovitz. So here's the idea. So suppose you have a function that takes n bits to m bits, so just some Boolean function. And a randomized encoding of this function is some new function, which we'll call f hat. And it takes in more bits than the original function. So let's say like r more bits. And it outputs s more bits than the original function. And this will be a new Boolean function that will satisfy a bunch of properties. So first, it should be efficient to generate the circuit for f hat given a circuit that can evaluate f. So this is just the ability to efficiently come up with this randomized encoding. And now the two really key properties are the following. So there exists some algorithm, which let's call it a decoder, such that if you randomize, such that for any choice of these r input bits, let's call that string rho, this decoder can take f hat of x and rho and always be able to recover f of x from it. So morally, what this is saying is that f hat of x and rho, irrespective of what this rho is, you can always extract f of x from this. It has the information about what f of x is contained within it, and there's some algorithm that can recover that information. And the second property is sort of like the other direction, which is to say that all the information it has is just f of x and nothing else. So this is to say that there's some polynomial time algorithm called a simulator, which if you give the simulator just f of x, so you don't give it x, you don't give it f, you only give it f of x, then the simulator can sample from a probability distribution that is close either computationally or statistically to the distribution that you would get if you randomize over this rho. So if you take f hat of x, so x is fixed, but rho is just a uniformly random string, then these two distributions have to be indistinguishable from each other.
Does the simulator have to also be able to know what rho is, or just?
No. Yeah, it doesn't know rho. Yeah, so it only knows f of x. And it has its own internal randomness, and it can sample from the same distribution that you get here, or close to the same distribution.
But it may not be able to reconstruct what their rho and x rho.
Yeah, that's right. But nevertheless, it still can sample from the distribution. Yeah. Yep.
Does simulator depend on f?
It can depend on f, but not on x. So only on f of x. Yeah.
Do you want statistical or computational?
Yeah, so this is a very good question. So you can have either. And sorry?
Sorry, can you repeat the question?
Oh, the question was, do you have computational or statistical indistinguishability? So you can have either one. For my purpose, I want statistical indistinguishability. And in fact, I can even get exact statistical indistinguishability. So the simulator will be sampling exactly from this distribution for the construction that I present here. Any other questions?
Sorry, I'm trying to wrap my head around what prevents me from just not using the extra r bits and just copying them to the s, if r equals s. I mean,
Oh,
it
so
looks like-
just outputting the randomness.
Yes.
So you could do that, but this property has to hold for like any randomized encoding of f.
I'm sorry?
So these properties have to hold for any randomized encoding f hat of f. Not sure if that answers. So you could do that, and I think that will be, yeah, that will be a randomized encoding if you do that. But it's not a particularly useful one because evaluating that requires evaluating f itself. Like it has the same depth.
So there's
as-
another property here that is not, what makes a randomized encoding
Yes.
useful?
So okay. So one thing I want to say just before that is that morally, this f hat is kind of an information theoretic equivalent function to f itself. And the interesting property is that you can construct randomized encodings that can be much easier to evaluate than f itself. So this is why they were considered in this paper, where they showed like the main result in this paper is that whenever you have a function f that can be evaluated by log depth circuits, it is always possible to construct a randomized encoding that is evaluatable in constant depth. And then that's useful because by this fact, like the equivalence to f, it means that, for instance, if f is a one-way function, then f hat is also a one-way function. If f is a hash function, then f hat is also a hash function. So like f hat inherits whatever properties f has, but it can be much easier to evaluate than f itself. Any other questions? Yep.
Just interesting you used the word morally. I guess what do you mean by morally?
Oh, like, you know, so, you know, this is the precise notion of what it means to have a randomized encoding. And I'm saying morally just as like, you know, in a hand-wavy sort of way or like intuitively, this is what I mean. I know that cryptographers like to use the word morally when they talk about things. Any other questions? Okay, so what we're going to do is we're going to construct a randomized encoding for linear maps, so things of the form m times x. And the randomized encoding will be evaluatable in constant depth and even by a 2D local circuit. And one thing that I'm not going to show, but it follows from these properties, is that the entropy difference under uniform inputs for the randomized encodings of two functions f and g is exactly the same difference as the entropies of f and g under uniform inputs. Yes?
Is this somehow the analog of subsystem codes? And
I don't know.
because it's like a gauge thing,
Uh-huh.
and then you get constant stabilizers or constant. I don't know. It sounds like.
I don't know. I don't know subsystem codes very well, so I don't know. But maybe we can talk about it afterwards. Okay. So here's the construction. I won't explain it in full detail because it is a bit technical, but I'll just give you kind of the high-level picture. So the idea will be the following. So from this matrix M that you start with, we're going to make a grid that's of the same size as the matrix, so M by N. And at each location of the grid, we'll have a constant number of random variables. And you should think of these random variables as you know, this like row string, like the extra randomness that you will put into the randomized encoding, and also some of the bits that will be output from the randomized encoding. And the point now is that when you get an input x, so the randomized encoding now you know, takes in as input x and some of these random bits from this grid. And the point is that what it will compute is it will just do some XORs between you know, like these inputs and nearby neighbors according to this grid, as well as XORs between like neighbors you know, like anywhere else in the grid. So just doing like, you know, looking at some of your neighbors and doing like additions with them. All of this is done like in parallel in like a few layers of depth. So it's just a constant depth circuit. And the point is that like each variable depends on or influences only a constant number of its neighbors when you do this. And what you're able to show, like if you choose these variables appropriately, is that you get exactly the properties of a randomized encoding. So for instance, if you imagine that you XOR the X bits into uniformly random bits in this like last row, then you're effectively one-time padding the input X. So you've kind of statistically hidden what the input was. However, you're choosing these variables so that if you XOR everything together, for instance, if I were to XOR all the variables in this last row, I will get the last entry of m times x. And if I were to XOR all the entries in like the rows from I up to m, then that would give me entry m times x subscript I, so like the ith entry of the output. So the point is that the output of the randomized encoding, which are these variables that are arranged on this grid, will look uniformly random, subject to the constraint that if you XOR them, you're going to get the output of the original linear function, so like m times x. So yeah.
Can you maybe start? I didn't understand this slide. What are the colors? What are the can you explain again?
Oh, okay. So the colors don't really mean anything except to denote the fact that there are different variables in there.
But how are the variables related to the qubits? Sorry.
Oh, so far this has nothing to do with qubits. Like this is a purely classical construction. Yeah.
May I ask a question?
Yeah.
I didn't understand what you said, but
Sure.
But let me just ask if this is what you're getting at.
Yeah.
You want to output the XOR for a large number of
Yes.
of bits.
Yes.
You don't have enough depth to do it.
Yes.
But now, are you saying? Well, what if instead you output a different set of bits?
Yes.
XOR is this XOR.
That's right.
But now you choose those randomly in some chaining kind of way.
Exactly.
And now
exactly.
you have, okay, so this is what.
Yes, this is exactly what's happening.
Okay.
Yeah. 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 So that's exactly what's happening here, and you can show that indeed, this like arranging the variables in this grid, and looking at the distribution of this when you randomize over these variables, that distribution will be exactly uniform, subject to the constraint that the XOR gives you m times x. So you get like this privacy property exactly, like not even approximately. Yeah.
Where is x appear? Like, does x appear in multiple rows? Like,
No, just the last row, because you want to have locality, right? So x, like you only XOR x into the variables of the last row.
And is the randomness of the encoding just showing up in like the way you one-time pad x or something?
Yes,
Okay.
that's right.
So it's also just in the last row.
Yes, yeah.
And I guess the matrix M itself is somehow encoded in the network here in
Yes,
some way that
yes.
is not depicted on the slide.
Yes, that's right.
Wait, sorry, I'm still confused. If
Yeah.
x is in the last row, then like how does the first row at all depend on x?
Yeah, so it doesn't. That's kind of the beauty of it. But if you want to get the the first entry of m times x, then you have to you have to XOR everything, like the entire grid.
Oh, okay.
So that
Okay.
because this decoding algorithm doesn't have to be local. Like this just has to be like any polynomial time algorithm.
Sure. Yeah, okay, I get it.
Yeah.
Wait, so how exactly does M affect the grid then? Like,
So like at each location, you will kind of conditionally add like its neighbors depending on what the value of m is at that grid location.
oh, okay.
Yeah. And this will have the effect of just like as if you had done a multiplication with m. Okay. Yeah, sorry, maybe I should have done a better job of explaining this, but again, morally, this is what's happening.
You can just black box what it does, right?
Yes, yes. Okay, so now if we put everything together, then we said that this first register we can prepare in constant depth because it's just a product state, and now we have this randomized encoding for m times x, with m being either the good code or the bad code, and so that is exactly what we'll prepare in this register. And because this randomized encoding has this property that it can be constructed by a 2D constant depth classical circuit, then this is inherited by the quantum circuit. So the quantum circuit will also be constant depth and 2D geometrically local to prepare this state. Yeah, and as I said, like the input register, you just need one layer of these y rotations by this angle in order to prepare it. And as I also mentioned, the randomized encoding, by virtue of being a sort of like information theoretic encoding of the function itself, it will preserve the entropy difference between the two cases. And therefore, if you have like a large entropy difference, then you will have it when you do this, this constant depth randomized encoding as well. Okay, and then to kind of circle back to what John asked in the beginning, so one application that you can consider that was considered in this paper by Boulang, Zhang, and Zhu is, suppose you're given the description of a local Hamiltonian and maybe also a cut across the qubits. And you want to ask, like, how big or small is the entanglement entropy of the ground state of this Hamiltonian across that cut? So what they showed in their paper is that for 2D local Hamiltonians, you can show that this problem is at least as hard as something called learning with errors, which is a problem that we believe is hard even for quantum computers to solve. And this holds for like higher dimensions as well, so like 3D, 4D, etc. But for the 1D case, they were only able to show hardness based on factoring, which, as we know, is efficiently solvable quantumly. So this only gives you classical hardness for this like ground state entanglement learning task. So with our result, we can essentially strengthen this prior result. So first of all, for the 2D case, I can just take this very simple Hamiltonian, which just applies a projector onto 1 at like each location, like on each qubit. And you can show that if you conjugate this Hamiltonian by the circuit that is preparing that pseudo-entangled state from the previous slide, then this Hamiltonian, its unique ground state is exactly the output of the circuit. So it's exactly that pseudo-entangled state. So then this means that for the 2D case, you immediately get hardness based on whatever you use to construct the previous pseudo-entangled state. And what's also nice is that this Hamiltonian is frustration-free and it has a spectral gap of 1. Whereas in the Boulang et al. Result, the spectral gap was inverse polynomial, and I don't remember, I think it wasn't frustration-free. Like, I think they used some sort of Feynman-Kitaev construction. So for the 1D case, I kind of just did the same thing. So I used the Feynman-Kitaev history state construction for this circuit C. And then you also get that the 1D case is hard based on a plausibly quantumly hard assumption, this dense sparse LPN assumption. But unfortunately, now in the 1D case, the spectral gap is inverse polynomial instead of being constant. Yeah.
Why couldn't they do this for their 1D case? Like, could they just have done Feynman-Kitaev like on their LWE hard Hamiltonian?
Oh yeah, like there is a key difference, which is that this result that I presented only works for like a fixed cut, whereas in their result they have this for like arbitrary cuts, and they wanted to get like an area law versus volume law difference in entanglement, whereas I don't know how to get this with my construction. So maybe if you like relax the task to just like fixing the cut, then maybe their thing from LWE could also be made to work in the 1D case.
And are these caveats also true for the 2D case? Like your 2D thing is only for a fixed cut, or?
Yes. Yeah. But I do wonder. So I haven't spent too much time thinking about this, but I do wonder if for the 2D case, it's possible to just take like some Hamiltonian and conjugate it by this circuit, and then immediately get this this hardness property.
The cut is just like the cut between the image of F.
Mm-hmm.
Could you like, I don't know, like have a random permutation that keeps
Yeah, that's a good question. So I don't know, but possibly. Yeah.
What's exactly the hardness assumption that you're using? Is this it's the related to the randomized encoding?
No, so it's this Dow and Jane assumption, the dense sparse LPN. So the inability to distinguish between a good and a bad code.
Mm-hmm.
Yeah. Okay, so in the remaining time, let me tell you like a quick backstory of this result. So, I've been thinking about this for a while, and back in 2024, when I was much younger, this Dow and Jane paper came out, and I kind of already knew, how to construct pseudoentanglement, but I was trying to do it from LPN, and I just couldn't do it. And then when this paper came out and I looked at the result, I was like, oh, this is exactly what I need to make my construction. The problem was that the construction that I had was much more complicated. So it didn't use randomized encodings. It used something called poor man's GHZ states, which were introduced in a paper by Benewatz et al. And these poor man's GHZ states are sort of like noisy versions of regular GHZ states. And they're useful for proving separations between like what you can solve with constant depth quantum circuits versus constant depth classical circuits. So I was kind of using them in the same spirit. But I never really bothered to write up the paper because I didn't like that the construction was kind of complicated. I didn't know if it had any interesting applications. But then this year I gave just a talk about it at Caltech. And it seemed that people found it interesting, and then I said, okay, maybe I should write up this result. But of course, we live now in the age of AI, so I decided I need to fully embrace the power of AI and use it to write this paper. So what I did was, this is kind of the work environment that I use. So this is Visual Studio Code, and I was just like writing the paper here, seeing the output here, and then asking AI about it here. So I'll actually show you on the next slide some prompts that I have. Yeah, I'm sorry that it's not super visible, but I can read out a little bit of it. So for instance, I had like a partial draft of the paper with my construction, and I would tell it like, I'd like you to rewrite the technical overview section 1.2 of this paper, to outline how I create pseudo-entangled states in constant depth from lossy trapdoor functions based on dense sparse LPN introduced in this paper. And then I said, if you look in the talk subfolder, I made a talk in which I outlined the whole approach. Use that as your guide. And then it basically just did that. Like it just like added a formal explanation and a formal proof of what I had outlined in this talk that I gave. But it wasn't perfect. Like it introduced some mistakes. So I would notice that it was skipping proofs of certain facts, and I would have to tell it, for proposition 2.4, you need to add a proof of this and put it in the appendix. And then it would do that. And then I would have to check it, and I would find that the proof is wrong. And I would say, like, I'm not sure this is quite right. And then I would explain, and then it would say, yes, your correction is right. The key point is blah, 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 and so on and so forth. So it was like a lot of back and forth like this. So eventually, like after a few days of doing this, like we arrived, like we were in agreement that the paper was correct and the result was presented in a way that I thought was reasonable. But I didn't really like, that I was using these like poor man's GHZ states. Like I felt like the construction is too complicated. And unfortunately, I couldn't find the original prompt that I gave it, but it was something like this, where I said, like, this is great, but I find that the construction is a bit complicated and hard to explain. Is there a way to simplify it? And basically, it just came up with the randomized encoding construction. So it proposed, like it said, instead of doing these poor man's GHZ states, you could just come up with like a 2D constant depth randomized encoding for linear functions. And then if you do that, it's much simpler and also might have independent applications in cryptography. So for instance, this 2D local constant depth encoding of like linear maps also gives you what are called low complexity cryptographic hash functions. So this is like an area of research that Benny Applebaum has worked on a lot. And that was quite interesting because the specific hash function that you would get from this construction is not something that was known prior, as far as I can tell, like from talking to people in that area. So it's kind of interesting that this seems to have like other applications beyond pseudoentanglement. And again, this wasn't just like a slam dunk. Like it suggested this, and then it gave one construction which was actually incorrect. And then I had like a lot of back and forth with Claude and ChatGPT until eventually we arrived at the version that seems to be correct, at least to the best of my abilities of checking it. And so, like the poor humans proposal has now been relegated to the appendix of the paper. So you can still see like my original construction. It's in the appendix if you want to have a look at it. Okay, so let me just wrap up. So first, on pseudoentanglement, there are still, of course, a lot of interesting open questions that one can look at. And by the way, I did ask ChatGPT about all these questions, but it wasn't able to solve them, at least not yet. So one is like, how large can we make the gap in entropy between the two states? So with my construction, I can make it logarithmically large, like on the order of log n, where n is the system size. But I don't know how to make it larger than that, or even whether it's possible. Another question is, can we get hardness of like computing the entanglement entropy across any cut instead of across a fixed cut? This is, again, something that I'm not sure is possible in constant depth because of like the limitations of constant depth circuits. I also have some ideas for how to use this to come up with constant depth proofs of quantumness, but the construction doesn't quite work yet. But I'm happy to talk about that if you have questions about it. And of course, the thing that started all of this is whether there are implications of these results to physics. Again, this is something that I don't know very well, so I'd be happy if people have suggestions about this. So on the use of AI, Umesh made a very nice point yesterday when I told him about this, which is to ask, like, to what extent is this randomized encoding that ChatGPT suggested actually new? So, like when I looked at it, I had seen like similar things, but nothing quite like this for this specific case. And I'm not sure. Randomized encodings were known, but people hadn't worried too much about like geometric locality or these things classically. Like they're usually fine with having unbounded fan out. So this is something that I didn't find, like looking in the literature. But Umesh pointed out that maybe I should search harder because maybe it actually exists and I just missed it. And I should do that and make sure that I cite the appropriate sources if that is the case. The other question is, yeah.
I think that maybe subsystem codes give you some kind of randomized encoding.
Okay, yeah, I'd be happy to chat about that.
In geometrical settings.
I see. Yeah, I'd be happy to chat about that. So one other point is, and this has been largely my experience with using AI, I found it very good at improving results, or if you have like a good idea, translating that idea into a proof or a paper. But at least so far in my experience, I've not had much success in like generating truly new results. Like giving it, like some open problem and asking it to solve it. I know that, in the news you hear about that more and more these days, but at least personally, I've not had this experience yet, unfortunately, or fortunately, depending on how you look at it. And of course, there's like the bigger question that people, I think, as a community or maybe as a species, should try to address, which is, how do we evaluate results that were obtained with the help of AI or maybe entirely AI generated? Yeah, there's a lot to unpack in this instance, I think. Okay, so I'll stop here and I'm happy to take any questions. Yeah.
First of all, another way you could think about this is you were trying to reduce the depth.
Yes.
And when you're computing parities, isn't it pretty natural to do this, where you just output something and you randomize it? So
This is, yeah.
Wasn't this so? I mean, couldn't you sort of think of it as a missed path rather than a
Yeah,
you know,
possibly.
maybe it wasn't. There was even a simple path, but once missed, it was missed, and then.
Yeah, I think that's a fair assessment.
Can you say more about why it's natural?
I mean, it's a known trick. I think this is a known way of handling things, and then the fact that if you chain, but you randomize, then that's you want to hide as well, right? So that's the interesting thing. And so the chaining itself is a known thing for you know
For reducing
for going to QNC or doing NC zeros, something like that.
Yes, that's right.
The randomizing is something that will hide it, but now you want to just put it together.
Yeah, so this is true. So I had thought about it, but the constructions that I was coming up with had unbounded fan out. Because, like in the randomized encodings that exist in the literature that do similar things, they typically have unbounded fan out. So usually they have they have the input interact with all the random bits or something like this. Like one input bit interacting with all the randomness or something along these lines.
As in they don't put the two ideas together.
Yeah.
The other thing I wanted to ask you, you said very nicely, that you weren't going to go with this DAO and thing, but you did incite us to ask you about it. So then you
So what they wanted to do was, it's kind of well known that it's very difficult to construct cryptography from LPN. So in particular, we know how to construct some simple things like public key encryption, one-way functions, but more complicated primitives that one could get, for instance, from LWE, like fully homomorphic encryption or lossy functions, this we don't know how to do. So they considered a version of LPN that has a bit more structure that would allow you to get these extra primitives as well. And essentially what they observed was that if you consider sparse LPN seems to let you achieve certain things, like maybe hash functions and stuff like this. But the parameters are very bad. Because when the matrix is sparse, it becomes easier to attack the LPN instance. So what they thought was, what if we try to hide the sparsity of the matrix by just taking the sparse LPN matrix and multiplying to the left with a dense matrix, like a random dense matrix. So then the new matrix that you get will now look like a dense matrix, but because now if you multiply it to the right by some vector, it's as if you're first acting with the sparse matrix on that vector. So you might inherit the properties that LPN gives you by first acting with the sparse matrix. And that was kind of the idea. So their conjecture is that the product between a dense matrix and a sparse matrix is indistinguishable from a totally random matrix. That's this dense sparse LPN assumption. Yeah.
I guess two questions. Maybe one to follow up Umesh's first question.
Yeah.
Is there a sense that, okay, I kind of forget, but this poor man's cat state,
yes.
isn't it also doing something that's similar
it is.
to breaking the parity into smaller things?
Yeah, so the thing is that with the poor man's cat state construction, I was doing the computation of this m times x in the phase of the poor man's cat state. Because you can act with poly z's on a G8Z state, and even though all of these act in parallel, you're getting the addition of all these parities in the phase. So this is what I was doing in that case. But I didn't know how to replicate this effect classically. And so initially I thought it's just not possible classically. And I wouldn't say that the randomized encoding construction is a classical analog of that. I think it's doing something different. It's not, the value of m times x is not actually computed in the randomized encoding. It's just that you can decode it from the randomized encoding.
I guess my other question, so for the first open question here, if I don't care about making my circuit geometrically local or 1D or whatever, Is there some big gap that's known in that case?
Oh yeah, so
Can I do any super poly n versus n?
yeah, so the largest gap you can achieve is like one state will have log n entanglement entropy and the other one will have n. So that's the maximal separation you can achieve. And that was achieved in like this Bouland et al. Result that I mentioned. Actually, I think even the original pseudoentanglement paper by Aronson, Umesh, Adam Bouland, Sumik, a lot of people, that one achieves this like log n versus n separation. And that's the best you can hope for. Yeah.
Just to follow up on that, do you know how shallow that circuit can be made?
It's log depth, I think. Like maybe Sumik or Umesh can. Yeah, it's log depth. Yep.
Recent applications of this poor man's GHC state for hardness of sampling.
Yes.
Do you think there's any relevance of this randomized encoding stuff to, like, is there a narrative of those results that's like somehow implementing the randomized encoding?
I don't know. That's a good question. I haven't really thought about it from that perspective. I have thought about whether, like using randomized encodings, we could get even stronger shallow circuit separations between quantum and classical. But I haven't thought about like viewing any of those results as somehow implementing a randomized encoding.
So I don't know, this is more of a comment than a question. Like the separation that Luke and I have in our paper uses these randomized encodings.
Oh, okay, great. Nice.
Do you think, because the intuition there is somehow like underneath everything you're using the shallow circuit to do like measurement-based quantum computation.
Right.
And there it seems like maybe you could have some sort of hope for having arbitrary cut, because it doesn't matter which order you measure the qubits. Though of course like it's kind of a different setting, because it's like if you just took MUQC and you trace something out, then it'd just be maximally mixed or whatever. So you have to do something extra on top of it. But,
right. Yeah.
But we were using these randomized encoding tricks there, so I wonder if it's useful.
Yeah, I'd be happy to chat about that. Yeah.
Can you say how similar your randomized encoding looked to this one?
It's pretty different. Like there, we were trying to hide a product of unitaries essentially, and so we just did this very simple thing where you like locally multiply every unitary by like G and G inverse. So like every unitary in the product looks totally random, but if you multiply them all together, you get the product of unitaries. That's the only thing that we're using there.
There's no further questions. Maybe we can thank Andrew again.
Thanks.